Hi everyone, my name is Brian Farrell and I'm a PhD student at Virginia Commonwealth University studying computer science. Today's video will be centered around calculating gradients from scratch using Numpy. The reason behind this video was because I had it as a homework assignment and I figured, what better way to learn the material and for other people to maybe learn as well as to record myself talking about it. This video is completely on the fly, so excuse like the slowness, or if I'm thinking, this is purely just me doing this raw. There's no editing, there's no script, there's nothing like that. So we will kind of go through gradient descent, what it is, some of the models that we'll be doing. So there's going to be five models that we will calculate the gradients for and update the weights, and then we'll dive into the code for it as well. So the homework was to create a n+1 dimensional vector model. So basically our model h of x with the parameters x and w will basically look like this, and really it's just a polynomial of the nth degree of x with the coefficients being the weights, right? So if n is equal to 2, then we have a second degree polynomial, and our predictive model looks like this. If it's 3, and I can kind of show like what they all look like. Yeah, so if n equals 1, this is our model. If n equals 2, this is our model, and so on and so forth, right? So we'll always have a bias, that's our weight with the subscript 0, and then as we go on, the polynomial increases, and then our weight matrix, we have a different weight matrix multiplying by r. So that's going to be how we are predicting our y. And so, gradient descent helps us find the right values for these weights and biases that lead to the smallest loss. So for this homework assignment, our loss is mean squared error, which is derived by this, or not derived, but the math notation looks like this, which you're basically taking your y estimate and subtracting from the actual y, you're squaring it and then taking the mean, right? And so how we do this with gradient descent is by picking a arbitrary point, basically having a random set of weights randomly initialized, and then we calculate the loss function from that. And then this is the whole back propagation. So we evaluate the negative gradient of the loss and take a step in that direction, right? So we start with random weights, okay? Then we calculate the loss. We calculate the gradient with respect to each weight, and then we times it by this learning rate and subtract from the old weight to get our new weight. And we do that. This is a iterative process, so I can kind of show an image of what it kind of looks like. So we start at some arbitrary point for a piece of data, calculate the loss, calculate the gradient with respect to the weights, times it by the learning rate, and basically the gradient of a function gives you the direction that increases that function. So we want to minimize, so we want to go the opposite, right? So eventually we'll go down to here. And then what we'll do is we'll recalculate the loss, recalculate the gradient, and all those same steps all over again to minimize our error. And so like I said, we'll go through some code. We'll go through Numpy, so this will be completely by scratch. There's not going to be any sort of gradient function or using PyTorch or anything like that. It'll all be from scratch. So if we take our loss function, which is right here, which is our mean squared error, right? Okay, so we want to take the gradient of this loss function with respect to each weight so that we can update our weights so that we can fit a better model. So if we take that loss function and come over here to our Word document, if it'll work. And there will be some editing in this video just because I don't want to have you guys watch me type all of this out. But basically, right, our loss function is our mean squared error. And really this should be squared, right? So if we were to write out that error, we get this. We get our actual y minus our predicted y, which ends up being this predicted y model, right? If we square that, you know, really if we write it all out, it looks like this. And then if we cross multiply, so if we do y and then multiply by all these, our bias multiply by all these, and then this part multiply by all these, we end up getting something really long like this, but this makes it a lot easier to calculate our gradients. Okay, so if we cross multiply it all out to get something like this, and then we add and subtract our like terms, we end up getting this, right? So now we can take our gradient of our loss function with respect to our weight. And in this case, in this model example that I'm showing, you know, it's just where that n was equal to 1. So it's just a 1, you know, the bias, and then weight 1 times x. All of our training data, which we'll show in the code later. So because it's easier to calculate the partial derivatives, we can basically, and I don't know to the extent that you know calculus, but basically the partial derivative of our loss with respect to weight 0, all we have to do is look at the ones that have weight 0 and then do our calculus, right? So we have, let's see if I can bold, yeah, this one, and this one. And so the gradient of our loss with respect to weight 0, we really just have to focus on these, right? So if we do this one, we end up just getting negative 2y. If we do this one, you know, the 2 comes down and we get 2 times our bias. For this one, we eliminate the bias and we end up getting 2 times weight, 1 times our training data. Then, to make it even simpler, we can factor out a negative 2 here and remove it, since it's a constant, outside of the summation notation. So we end up getting minus 2n times the sum of this little calculation right here, which is really just the error. So this ends up being negative 2, here, we'll put a in there, times the sum of our error, right? So if we go back to our PDF file, which basically has some of the formulas in our models, we have that right here. And in general, this flows kind of like this, where the partial derivative of our loss with respect to any weight for mean squared error is going to be minus 2m, and really m and whatever, times the summation of our error times x to the I to the power of j, right? So whatever weight we are finding our gradient for, we end up, that ends up being the exponent for x, right? So since our first one is weight 0, technically we get xi to the power of 0, which is just 1, which is why you get this is just being the error, right? But if we keep going with that general kind of formula, if we're calculating the partial derivative with respect to weight 1, then we have the error times xi to the power of 1, which is just xi, right? So if you can see the difference between this one and this one is we're multiplying it by our training data. And then so on and so forth. If we want to calculate the gradient or the partial derivative of our loss with respect to weight 2, which why would we have a weight 2? Well, in this model, we do, right? So in this one, we would be calculating the gradients for 3 weights. For this one, it would be for 4 weights. This one 5, this one 6. And each one's different. It just adds on a whole new element, like weight 3 or weight 4, and then x to the power of whatever n is, right? So if we're doing weight 2, then x is squared. If it's weight 3, x is cubed, right? And we keep going down that same kind of path. So this is how we are calculating our gradient, right? So we have, like I said, we have our loss function. We calculate our gradient, and then we take that gradient and we times it by a learning rate, and then subtract it from the old weight to get our new weight. And after this segment, I will show the code of kind of what this all looks like and how it's an iterative process. So now I want to show the code for calculating these gradients and updating them for each of our models. So if you remember, we had 5 models that we are fitting a line towards. Some are simple, and then it goes up in complexity as n increases, right? And so without any sort of easy helper functions that you know are friendly and calculate the gradient for us, I want to do this, do kind of everything by scratch. There's obviously an easier way to code all of these, but I hopefully am showing like every piece to the puzzle, and hopefully nothing is confusing or anything. So our packages are really just these. I don't even think I need this one, but we want PyPlot so that we can plot our models, our fitted models with a line, and then everything is just in Numpy, right? So we can run that. So below here is we have our training data and our y values, right? So we run this and then just kind of plot it. So this is our data, right? We have a chart in red of all our x's and y's, okay? So for calculating the partial derivatives with respect to each of our weights, I have, you know, the 2 functions that do that right here, right? So if you remember, our bias was the only one that looked kind of different. I really don't have to separate these because I could just set the weight to being 0, but you know, it still shows that there's a difference between the bias and the weight. So I have a function, dldw, that takes in our training data and our model that we want, which is going to be this variable y estimate. And then we have our weight variable, which is, it doesn't have to be called that, it's just going to be what our training data is to the power of. Because if you remember in the formula, you have basically the gradient is the -2 divided by m times the summation of our error, and then it's multiplied by the training data to the power of that J number, right? So M is going to be the total amount of values that we have in our training data. This is just an easy way to have the for loop where you set this variable equal to 0 and then you take the sum of it, right? So like we have in the formula, we have our y, and then we are subtracting from our y estimate, and then here, let me just, all right, I think we're good. And then we're multiplying it by our training data to the power of this weight, which is just going to be a number 1 through 4 or 1 through 5. But this is our derivative of our loss with respect to whatever chosen weight we are doing. And our y estimate is going to be our predicted y values for one of the 5 models, which is just polynomial. Same thing with the weight. There's really no difference. The only difference is this function doesn't have this part right here. And then we have a plotting function which takes in our new weights after we calculate the gradient and make the updates, our new intercept, and then n is just something for the charts. And to make it a little bit easier to read, we can have this for loop right here, which is basically going to draw us a line, which is not really a line, it's just a lot more dots within this range. That way it'll be easier to see like a fitted line for our actual data. So if I go ahead and run this is setting our weight matrix, and I went ahead and just put it all within a list of lists. So for our, when n equals 1, we only have one weight, which is weight 1, and then the bias won't be included. I'll include that right here. And then basically if n is equal to 2, then we have 2 weights. So I can go back to the PDF. So n is equal to 2, we have our bias, and then we have weight 1 and weight 2, which is going to be, here I can overwrite, yeah, which is going to be, this is weight 1, this is weight 2 of our n equals 2 model, right? And this is just random initializing of the weights because they're going to get updated after you calculate the gradient and multiplying it by the learning rate, right? So weight matrix, I don't have to include it all in one thing, but I do. This is for all 5 models. The weights for this model, the weights for this model, the weights for this model, okay? So for n equals to 1, which has basically been the example that we've been going through, if I were to just run this, right, we have our randomly initialized weights, we have our y estimate, which is our model, which is our intercept plus our weights times our training data. And we let's just say, you know, learning rate is 0 and we go through this once, right? It's basically going to fit like this. So obviously it's not going to fit our data very well because we're starting from random weights, so it's going to be a bad model. But what happens if I change our learning rate to a number like that and do it 10 times? All right, that's obviously better. It's getting closer and closer to fitting our data. And the behind this like kind of for loop is, you know, for 10 times this is our model, and we want to take our weight, this is our old weight, we want to subtract it from our learning rate times our gradient, and then the same thing for our intercept, and then we want to plot it and kind of print out what our new weights are, right? So the more I do this, the more it's going to fit that line eventually. And I can kind of, let's restart this, go back, and let's do it 200 times. And boom, You know, it fits our data very well, right? So it's an iterative process. It's not, you know, I wouldn't say like learning, but it's math. It's calculus. It's taking the gradients, it's updating the weights, and then it's fitting our line, right? So for our second model, where n is equal to 2, we have our y estimate, which is this. Okay, so we have 2 weights and then our intercept. If we were to do that, it fits our line kind of nicely. And then the same thing for our third model, right? It fits it. Our fourth model, it fits it. Our fifth model, right? It fits it. And it's taking each of these different polynomial equations and fitting the line based on our data and based on running this gradient descent, right? So pretty cool. It was fun coding this and doing this from scratch, which I've never done before. So this is kind of a learning opportunity for me. If I messed up on any of the math notation or with the code, or if you have questions, comments, you know, feel free to let me know. Feel free to like and subscribe if you want to see more. I plan on, you know, doing more with my homework, with my personal research. I'm specifying in natural language processing. So there will be a lot more videos to come, but hopefully this is good, and if you have any sort of feedback of how things can be better, then, you know, please let me know. But there are obviously packages out there that can do this a lot easier, and in the real world, you know, your model won't look like this, but it's pretty cool to code and kind of practice. So thank you so much, and I will be posting videos maybe on a weekly basis or a bi-weekly basis. I don't know. This is just kind of fun for me, and how I'm hoping to learn more about this. So thank you.